Okay, so where is that darn record button? You know where the record button is?
It tells me it's already recording.
Oh, it does.
Yes.
Hey, it's not telling me that. Why would that be? Okay, as long as it says it's recording, that's the important thing. All right, got 13 people here. All right, we'll give people another 30 seconds here and we'll get started.
Sounds good.
All right, so let's go ahead and get started. Well, good morning, everyone. I'm here with Jennifer Herron, CEO and founder of Action Engineering. My name is Mark Thomas. I'm the executive director with the DMSC. DMSC is the organization that puts out these monthly webinars, all primarily QIF centric. And we're going to have Jennifer do a presentation for us today, and I'll let her introduce her subject and herself in just a moment. But before we get started, let me go through a couple of quick points on housekeeping. Those of you that want to ask questions about what we're going to be doing, you can go ahead and do so at any time. We're going to hold the questions and answers until the end, but on the right-hand side of your control panel, your GoToWebinar control panel, you can see there's a section there that says questions. Type your questions in there and we'll cover those questions at the end of the session. The other thing is that everyone that is participating with the webinar today will get a recorded version. That recorded version will come to you tomorrow, probably by around noontime. And we invite you to go through this if you wish to pick out points that you really wanted to cover very closely. But more importantly, we are asking that you share that video with some of your colleagues that may not have been able to make it to this session. So let's go ahead and get started. We have Jennifer Herron. Jennifer, go ahead. Thanks.
Great. Thank you, Mark. Thanks everyone for joining us today. I know it's summertime and everybody would rather be out like by the pool, including me, but you know, hey. So welcome. Thank you to Mark and to the DMSC, which is the Digital Metrology Standards Consortium, for inviting me to present today. I'm going to tackle a topic around bill of characteristics and how that can be your catalyst for your digital twin. A little bit about myself. I'm the CEO and founder of Action Engineering. I am also a DMSC board member. This is actually my 5th year of my second term. So I'm in the second term of being a board member with the DMSC. It's been quite fun, and I definitely learn a lot from the folks that I work with. I also volunteer for other standards organizations in addition to the DMSC. And the important thing about that is that when we volunteer and other board members also volunteer in other standards organizations, we're able to liaise between standards and make sure that what we're doing at the DMSC is complementing what's happening at ASME or ISO or AIAG or SAE. So we try to hopefully we try to make sure we aren't replicating or muddying the water for any other standardization that can be going on within 3D data interoperability, and I'm hoping that we're serving you guys as an industry. So at Action Engineering, we're in the business of guiding organizations to use 3D data to communicate across their enterprise and throughout their supply chain. And we know that it's imperative to engage all the stakeholders to use, reuse, and innovate with digital twins. This is very cool technology, and it no doubt saves time and money during production, but the people who are actually doing the jobs with drawings today have to know there's more than just like a cool VR headset in it for them. So there is lots of benefit, and hopefully we're going to see some of that and prove it out for you today, kind of the geometry proof style. But this 3D data transformation techniques help increase communications, which is really important because typically we have siloed departments, just engineering and quality, that really aren't talking to each other. And studies show that companies and organizations that communicate effectively are 4.5 times more likely to retain the best employees. Pretty important statistic these days especially. So this is pretty big if we increase the communication. And that's the job that we're in at Action Engineering, is to help you increase your communication. So hopefully you can implement some great technology, get a big return on investment while attracting and retaining the best talent. All right, well, I need to align some nomenclature. And so let's just start with the digital twin definition. I realize somewhat contentious to have a real definition on the screen here, but let me just paint the picture of what my favorite definition is. This one actually comes from the CMM PLM glossary, and it says that a digital twin is a physics-based description of a system resulting from the generation, management, and application of data, models, and information from authoritative sources across the system's lifecycle. I like those words, not sure if you will, but here's a couple other alternate definitions, one from Siemens and one from the DAU. You know, the reason I like the CMM one is that it's this holistic enterprise focus. It describes a concept. It's not really just a thing. So it's really kind of hard to define what a digital twin is. For the purpose of this presentation, I'm thinking of the digital twin as a concept rather than a discrete definition of some particular piece of data. So if you are super geeky like me and you want to dive into some digital terms, you can check out our latest evolution of our dictionary tool and search terms to your heart's content. And if you want to play a little game with me and drop into our chat window here, go over the dictionary now and search for the term model and product and drop in how many terms actually show up for those two words. So in case you're a little confused about what a model is or what a product is, don't worry, so is everybody else. All right, so the second definition is model-based definition, not model-based design, but model-based definition. We get a lot of confusion with these MBDs. Sometimes you get model-based depression around all of the MBDs. I know I do. So model-based definition is how we capture product definition data as 3D data. this is inherently digital, so it's all part of your digital enterprise. My hierarchy of model-based definition and quality digital data builds on other standards like the ASME or JADA frameworks for MBD data. ASME is the American Society for Mechanical Engineers, and JADA is the Japan Electronics and Information Technology Industry Association. So I like to constantly look at the latest standards, integrate this into the best practice and approach that we'd like to share with people. So both of the organizations that I mentioned, ASME and JADA, are working with the DMSC, which brings you QIF, on standardizing and codifying the concepts of digital twin, model-based definition. So quick shout out to all volunteers at all those organizations that make these kind of standards available to the industry. All right, diving into the details and the fun stuff and where we get some return on investment metrics and benefit messages. We all know, guessing you are all painfully aware of how difficult it is to find return on investment data for any digital twin initiative. So really what it comes down to, and this is what we've discovered at Action Engineering over years and years and years, is it comes down to evaluating particular use cases within your particular business scenarios at your organization. You could go benchmark other companies, but you end up not believing it or talking yourself out of the fact that, oh, well, you know, they build backhoes and we build jet engines. So those are two completely different things. We can't share the benefit metrics. So hopefully this will give you a framework for 2 use cases you can use to dive into your return on investment. Okay, so the 2 use cases I'm presenting here, these are daily operations that happen at every manufacturer all day, every day. So the first one is automated bill of characteristics generation and interoperability. We can call this 3D FAI, where FAI doesn't actually mean, or it doesn't have to mean, frustration always included. It means first article inspection. And then the second use case, automating engineering changes while maintaining traceability. Suppliers tell us that processing engineering changes is their #1 pain point. So let's call this the digital twin of engineering change control, maybe. And then I'm shortening engineering change to BEC. So both of these use cases are going to use QIF as the interoperability conduit to connect engineering and quality data together. So starting with the fun stuff, here are the metrics right up front. These are the real savings that I've calculated from 2 workflows that you'll see in each of the demonstrations. #1, for 3D FAI, 75% time savings for engineering and quality personnel. 100% reduction in manual data entry, thereby decreasing the cost of poor quality. And then 100% increase in design to inspection data traceability. That's a lot of savings right off the bat. That's just with the first article inspection. Now, the second one is around engineering changes, and this is a concern because we all know you have engineering changes all day, every day, even after you do your first article inspection, and this is the concern. So in this engineering change process, not only do we maintain the traceability at 100% level, we have a 50% time saving during that engineering change. So we're maintaining the traceability, we are saving time, and we're reducing manual data reentry. All right, so those are the upfront metrics. Hopefully I'm going to prove this out sort of, like I said, geometry proof style. Before we go on, those were like the hardcore metrics, but there's also these little intangible things all over the place with digital transformations, as you guys know. If we hone in on these 2 use cases, here are the 4 benefit messages that you can share with your business to go above and beyond those hardcore metrics. So if you're interested in the digital twin concepts, which I'm sure you are, that's why you're here, and establishing digital thread feedback loops, these feedback loops are the big deal, then we focus on the model-based definition that's made interoperable by QIF to establish an interoperable and automatable bill of characteristics. And that bill of characteristics is what I said we were going to focus on today, that maximizes your traceability. So if you're working really hard to create good GD&T as 3D annotations, then that good data demands good interoperability. And that's why GD&T was invented, and now MBD, model-based definition, combined with QIF, makes that process digital. And that speeds up time to market and decreases quality escapes. And if you don't know how to make good GD&T with 3D annotations, that's okay. That's what we do at Action Engineering. Let us know and we can help you out there. All right, I am going to switch over and play a movie for you. So bear with me 1 second while I do that. And I'm going to go ahead and play the movie. This one is a little bit long. It's going to run about 15 minutes, but this is going to give you the whole workflow of the 3D FAI process from start to finish, using the digital twin concepts and focusing in on that digital bill of characteristics. So I'm going to turn off my webcam, turn off my sound, and let the movie speak for itself. And I'll see you back here in about 15 minutes. Let me paint you a picture of your current state and then describe the steps it takes to hand off information from engineering to quality for the purpose of performing a first article inspection. First, a drawing is generated. That drawing is ballooned. A quality planner uses the drawing and balloons to generate an ISIR form or an FAI form. Then they use the drawing and the form to create a measurement plan. This is mostly a manual data entry process today. The quality plan is passed to a CMM programmer to create a machine code program to measure the part. Then the measurement is performed on the CMM, and sometimes there's a need to supplement the measurement plan with additional measurement resources. All the measurements are recorded in the ISIR or FAI form, and finally, the part is accepted. So I hope I generally captured the way you work today. I estimate this work takes roughly 6 days from start to finish. Let's see the workflow and potential time savings when using MBD plus digital metrology techniques together. Just like you did with a drawing, you'll still need this step to generate the MBD or model-based definition. Use your preferred 3D CAD platform in this step, and we recommend training your MBD authors to use GD&T per the latest ASME and ISO standards to maximize the digital metrology savings. Use CapVidea's MBD Video software to auto-generate the balloons and a table which captures the bill of characteristics. The quality planner uses CapVidea's MBD Video software to auto-generate the ISIR form to ISIR. Then the MBD is imported into digital metrology planning software. And today we're going to see Calypso from Zeiss, where the user of the software does not enter any data. Rather, he just imports it. During this step, they identify that the GD&T is best validated using a CMM and an X-ray device to check the overall profile tolerance on the cast surfaces. Next, the CMM programmer checks the automated path plan, probes, and simulates the planned path to measure the part. Then the measurement is performed on the CMM and with the X-ray. All the measurements are automatically recorded in the ISIR or FAI form. And finally, the part is accepted. This workflow only takes about a day and a half as compared to the 6 days before. This is a 75% time savings. Does CMM programming cost you significant time and effort? I'm guessing your answer is yes. This digital thread technique I will teach you today can save up to 75% of your CMM programmer's time. I will show you a part that has some complex geometry. The part is fabricated as a casting and is then machined to produce the final product. We're going to see a Creo model that has annotations semantically associated to its geometric features. Sometimes we call this PMI. We're going to see why QIF is the key interoperability standard to the door of this digital opportunity. We're going to see how Zeiss leverages a digital bill of characteristics to program their CMM. And we're going to see the coordinate measurement machine in action. We'll also see how Zeiss's X-ray equipment, Metrotom, rounds out the measurement plan by scanning the complex geometry, which is defined as an overall profile tolerance. This is an average complexity part. This part starts life as a casting and is then post-machined prior to going through the PPAP process.
So here we're looking at the PMI. I mean, this is the data that should be driving our PPAP process downstream. The way things are done now is that, typically all of these requirements exist on a 2D drawing, and you have to have an engineer go through the drawing and read these annotations, interpret them, and then somehow place them into a spreadsheet. This is a lot of work. Obviously, it's a lot of interpretation, and it's all pretty unnecessary. What we're going to see in this workflow is how you should be placing your product requirements as semantic PMI and then allow that data to simply be reused.
While in Creo, the MBD-Vidia plugin makes the export to QIF as simple as 2 mouse clicks. Depending on your operations practice, your internal manufacturing or your supplier can use the QIF file to automatically perform the ballooning step. Once the QIF is exported from Creo, then we use MBD-Vidia to automatically generate the balloons and bill of characteristics. The automated ballooning process eliminates time spent in manual data re-entry. Now that the engineering requirements are digitally identified and a bill of characteristics is made, I can easily and automatically generate an ISIR form using MBD-Vidia.
Yeah, this ISIR form is really just a sample of what a typical PPAP inspection report might look like. Usually every company is going to have their own look and feel of how it should look, but in essence, I mean, what we can expect is a list of all the characteristics that need to be measured, along with the quote-unquote balloon numbers that correspond to each of those characteristics. And the other thing is that, as we're seeing here, when we do this in the context of an MBD workflow, it's easy to create a sort of MBD-powered Excel spreadsheet like this, which is kind of enhanced. I mean, it includes the model saved views to give a quick snapshot of what each balloon means, and it's all powered by hyperlinks within the Excel and so forth. So, in a way, this is kind of like MBD using Excel.
Let's just load our QIF model here in Calypso, and you'll kind of see how it does look a little different than a traditional model without any PMI or MBD based models. So the nice thing about the QIF is you really don't lose anything. You can do everything that a CMM programmer is accustomed to doing in the past, and a lot of that work has already been done upstream. It gives the software the ability to extract these features, link them to the appropriate dimensions, and assign the tolerances and datums appropriately automatically. So it really cuts down on a lot of that time-consuming clicking that the CMM programmers typically used to doing. But obviously the programmers still needed to handle a lot of the navigational movements and setting up some alignment. Once we have this orientated, we can actually generate our measurement plan. And we are going to generate all the PMI, and this is really where you'll see the time saving happen. This is going to do a lot of the work that is typically done by the programmer, but it's a lot of the kind of monotonous work. It's a lot of the clicking and associating and things that are not fun to do as a CMM programmer. You want to kind of more focus in on the navigational movement. So I'm going to hit create, and you're going to see it bounce around over the model. It's going to actually be extracting all the different surfaces, planes, cylinders, and associating them to their dimension. We can actually jump right into setting up their strategies. So we want to kind of say, okay, well, what probe do we want to measure this with? What clearance plane do we want to navigate through in order to measure? And then kind of how many points do we want to take? And is actually use another one of our tools to auto assign our Stylus system. What we're doing is we have a Stylus system, a star probe here that has 4 tips in order to measure all these different features. What we can actually use is our automatic Stylus assignment. And what it'll do is it's just going to go through our entire program, look at every single one of these features, and assign what it believes to be the appropriate Stylus. And we can actually run this through simulation to kind of give us a preview of what we're going to see on the machine. All right, so we'll see our Stylus system come into view here, and now we'll see it run just as it would on the CMM. I'll turn up the speed a little bit. But you can see it how it's going to just trace around in all of our paths. So everything that I just did, I mean, as I mentioned previously, I mean, that would have taken probably a few hours at the very least, and that's for an efficient programmer. I mean, if you're new to programming, we're talking maybe a day or two to really kind of make sure everything is set up how you'd like it. So everyone programs at different speeds, but this removes a lot of the programmer error. Now, you're not worried about mistyping a number in or something like that, as well as improves the time it takes to do the programming. So it's really just a very helpful tool as a Cmm programmer. That is the end of our simulation run, and what I was doing while that was running is I was just kind of noting the areas that needed to be tweaked. Would have had a few collisions there. I mean, with any program, the first time you write it, you always make a mistake. That's just that human error, but that's what the QIF side of things will help eliminate a lot of that. Well, and in the QIF environment, not only do we accept the QIF model in, but Calypso does have the ability to spit out your results in the QIF format so that we can then bring them back into a software like NVDVidia or something else. So what I'm going to do for this program is here, I will turn on QIF result. That way then, after I make these changes, when we run it on the machine, we'll be able to get that file and kind of show that workflow of everything going back into NVDVidia. All right, and you'll be able to see the measurement plan kind of running through here. We sped it up just from a time-saving standpoint, but this is like any CMM programmer or machine operator. I mean, you're used to doing this on a daily basis. You can see it's very similar to our simulation run that we did previously or a few minutes ago. It's just gonna kind of be the actual scans here. So we'll get the QIF result file once this completes, and we'll jump actually into the Metrology CT dataset portion of the program to show that next before kind of looking at the overall results. So we'll let this wrap up here though. This was scanned on a Zeiss Contura with an active VAST probe head. For those of you that are familiar with our CMMs, the different models and things like that. The last little bit that needs the attention is actually generating our freeform surface on the CAD model here. You can see all this purple area here is where we would want to measure for a surface profile. Now this is a very difficult measurement on a CMM just because, as I mentioned, you can't get a tactile probe to really touch off on all that area. You could, but it would take an extremely long time to scan. So a CT data set analysis like this is going to be much more ideal from a time standpoint, and you can actually check all those little nooks and crannies. So what I'm going to do is just program the strategy here to cover all those little areas. And you will see the software just assigns the nominal points all over all the selected area here that we want to check. And last but not least, we just have to load the actual CT data. So I will go ahead and do that now. What we have is an STL file, so we will load this. This actually comes from our Metrology system. It was ran over there before this, and we can do all the evaluation offline here on this separate computer. All right, so you can see our CT data set has been read. It is actually here, you can see it floating in space. The last thing we need to do is just align it to the model and run the measurement plan. So I will. All right, and then once you align it, it will match those datums up to the datums on the CAD and actually begin running the measurement plan here. And as it's running here, you can see the vector arrows there kind of bouncing around the part as it's checking each of the individual areas. So you can see this freeform surface is going to be checked much faster here on the CT data set than if you were physically scanning it with a tactile probe. And at the end, we'll get our PDF. You can see we are passing here on GP36 and GP32. But the PDF report, maybe not so much what we're looking for. Personally, I'm interested in the result QIF file. This is what we'll then pull in to our MBD Vidya or some other third-party software to actually pull these results and bring them full circle.
Thanks, Charlie. Yeah, so this is Daniel Campbell. I'll walk you through now the portion of importing these results from the CMM and from the CT back into the QIF MBD model, so that we can kind of view this, full round trip and get the results back. We will insert first the results from the CMM measurement here into MBD Vidya, and so we'll go ahead and do that. We'll select Insert, choose the CMM results. We'll make sure that these results get connected back with the MBD data, and there it is. So what we're looking at, we see that the blue lines that we see are actually the scan paths. So if we zoom in there, we'll be able to see, if you zoom in enough, you'll end up seeing separate individual points, each of the points that was gathered by the CMM. And in the bill of characteristics, we'll see each of the measurands, each of the features and characteristics that were measured. And as we select each of those items, we could see the result that was measured on this CMM. So we start to see some of the results that were brought in from the Zeiss Contura CMM. Okay, so now what we're going to do is we got to import those CT results. So we go through the same steps. We select our CT results though this time, and we act to reconnect that data back with the MBD data. So now we have imported those results, and we can see the measurement points that were created in Calypso from all that CT data, and we can look at those couple of tolerances, those general profile tolerances that were measured with the CT device. So this is kind of the profile tolerances that are measuring larger or more irregular surfaces. Often you might find this covered with unless otherwise specified or something like this. So yeah, in this case, it's a great use of the CT device. And in the bill of characteristics, we see our CMM results on the left side, and then the X-ray CT results are there in that right column, just sort of all nice, neatly organized and tied back to the MBD.
Well, I hope you guys enjoyed that video. I'm going to switch back now to my screen. There we go. Great. All right, so you should be seeing just a snippet screenshot of that video again. That full demonstration is available both on YouTube and in our knowledge MBD system called Oscar. So if you want to go to our website at action-engineering.com, you should be able to navigate to those spots. I've also included those links into the chat for you folks. So I know there was a lot of information in there. I hope you got some questions going for me. We will take questions here at the end as we because there's a lot of devil in the details. Some of you guys have already asked some great questions, so I tried to answer those. Let me go on to the next use case. So this is engineering changes, 3D engineering changes, and let's take a look at how long it takes you today. So I've estimated that it takes on average for each process step to be accomplished, it's roughly like 8 hours a day to do each of these boxes. So that's talking about eight days. Some simple parts may take less time, some more complex parts than what we have described here may take a little bit more time, but just kind of taking an average. something that's pragmatic and practical, and you're not going to throw all these numbers back in my face. So, and some industries may have more steps than others, and they may have less. So we've just tried to take a snapshot in time and kind of averaged out so that you guys have something realistic you can share with your bosses, with whomever you need to convince that this is a valuable thing to be doing. We're assuming this average complexity part takes about 8 days to complete the process. We're creating a drawing, ballooning it. The quality planner is going in, adding little balloon numbers on there. Sometimes you guys are doing them with a pen and paper. Some of you have a little bit more sophisticated methods, but nevertheless, what we've done in the process that I just showed you is to balloon that in an automatic way. So now what happens if you've completed your first article inspection and you come up with a variance or nonconformance that has discovered during the measurement phase, and so then the inspector has got to take that variance back to the engineering agency to perform some kind of corrective action, and you've got all this digital data you've set up. What do? It makes you very nervous. I totally get it. Makes us nervous too. So this next workflow and demonstration will describe how, once you've completed the first article inspection and you find something wrong with your parts and you need to go back and make an engineering change, how we can simplify and automate that change process. And so gonna play you that next video. The savings that we're seeing here is roughly a 50% savings because we're able to eliminate the ballooning step, the ISR or FAI step, the revising the MBD step, and then creating that Delta FAI form. So let me share one more video for you. I'll cross my fingers that the audio plays for everyone. I know it's been a struggle for some. As an automotive engineer, you need to know how your parts are built. The measurement results you receive from the PPAP process are crucial. In this case, something is wrong with this batch of parts. The quality department must send the reports back to engineering so they can make a change. Because we have digitally encoded characteristics that are semantically connected with the surfaces and features they represent, both engineering and quality are able to access all the data, which empowers their ability to work better together to determine the corrective action or to reconcile nonconformities. In this situation, engineering and quality review the 3D results together and determine how to reconcile the nonconformities seen during first article inspection. Together, they agree on a change and decide to open the tolerance of the slotted holes and document that directly in the MBD. They also decide together that it is acceptable to have an increased tolerance on the radius, and engineering also makes that change. The people that work in engineering and quality now can trust the data because they can visualize the results in 3D, and thereby they have a better understanding of the issues to determine a path forward. In short, they can make data-driven decisions. When all parties are empowered with digital data, their products are much better and higher quality. Oh, and they get built and inspected faster because we have eliminated manual data entry. Bolstered with effective quality data and a digital and fast feedback loop from quality, engineering makes the changes and releases a new revision. What is really powerful about QIF that is powered by MBDVidia is that once we have a new released revision, we can now release a revised QIF file and then see the Delta revisions. So we're not having to redo all the work from the first time. Following good practices when issuing changes as MBD, I automate the comparison of the original design with the changed design.
Yeah, so the general workflow here is that we're comparing the past revision of our model to our current revision, and Interoperability reveals everything that has changed. And then from there, it's the user's job to review all the changes, all these changes that have been identified, and mark them as either intended or as unintended. Intended changes are, of course, what we're looking for. And any unintended changes are caused to go back and see what went wrong. Why was something unintentionally changed at this point? Now, this is a really important step for MBD, because when your model is such an important part of your manufacturing enterprise, you better make sure that your model is correct, right? I mean, what we found in practice is that our users find unintentional changes creeping into their models on an everyday basis. I mean, this is very, very common. So this is an important check to be making. Yeah, and then finally, as we see here, we have a nice summary report at the end, which shows us the status of our revision comparison. In this case, all of the changes were intended.
Normally, when receiving a revision, the quality planners and metrologists spend hours creating a Delta ISIR report. It's just a ton of work. But using MBD Vidya and QIF, the metrologist can easily process a revised bill of characteristics that shows what has changed, and then issue a revised ISIR form.
Yeah, so the point here is that we've already established that certain characteristics are, shown to be intolerance. So, this delta step's about fixing the tooling for the non-conformances and then proving that those adjustments to the manufacturing plan are adequately solving the problems. So this is a pretty typical process. But again, I mean, looking at the today's, typical 2D drawing-based approach for how to do this, this is a very time-intensive process. I mean, basically, someone just needs to go through the drawing for each of the two revisions and figure out manually what's changed. But really, I mean, that data, it should exist on the MBD, and you should simply reuse that data. So really, none of that extra work should be necessary. It's all a natural part of an MBD workflow.
Check it out. Only the items we changed are highlighted, saving both the supplier and the OEM time and money. Looking at the measurement results on this revision allow you to examine if there are any nonconformances on any of the changed characteristics on the design. We make it to acceptance. The revised design yields better parts than before, and the product is ready for its full production run. All right. Hope you enjoyed that. I was so excited we got the product over to acceptance. So, hey, sometimes it takes a really long time, right, guys? So again, full demo available on YouTube and in Oscar. If you want to click on over to that, in Oscar, you can create a free account and have access to lots of other content as well that has a lot of industry learning. It also will give you insights into our Creo how-to course, which is how you actually author all that data so that you can leverage these cool downstream techniques. All right. So I know that I am super grateful that the cars on our roads especially have quality teams at automotive producers that are focused on really high quality parts. So, and that goes for jet engines and all the other products that we use in the world. So when we work with your team at Action Engineering to implement MBD for design, fabrication, and inspection activities, we see tangible benefits within these three typical silos because they're building good cross-functional relationships. And we're layering in organizational change management techniques with the technology, tools, and process change that's required in order to hopefully get you guys to have good ROI and get these benefits. So when you combine MBD plus digital metrology, you're not only saving time and increasing data quality, but now also quality teams, these are the actual human beings, get to contribute to the time savings rather than being the bottleneck. And this is a really, really big personal win for individual quality engineers. So I know you guys also heard some guest ghost speakers that aren't here with us on the webinar today, and I want to acknowledge their contributions. So we thank Daniel Campbell at CapVidia and Charlie Tersch of Zeiss for supporting these demonstrations that I showed you today. We actually spent lots and lots of time preparing these for you to hopefully make sure that they were clearly stated. So reach out to any of us if you have further questions, or if you need me to connect you with Daniel or Charlie, I'm happy to do that. They're fully aware this webinar is going on, so they look forward to your connections as well. I am about to take questions, and I'll just close with a little bit more about who Action Engineering is. Our goal is to digitally connect your manufacturing lifecycle. We do that by charting your 3D path from requirements through sustainment. We don't want to forget about our friends in sustainment, because that is a massive part of your activities. We have a strategic program that comprises a 4-step process. We call it Ready, Set, Go, and Grow. Super simple, but lots of nuance and complexity in these transformations. And that strategic program creates manufacturing resiliency, and we tailor it to your unique attributes of your company. In addition to this strategic program that we offer, we have Oscar, which is a curated toolkit of 3D standard compliant learning. And Oscar becomes the atlas for that Ready, Set, Go, Grow framework. And our experts at Action Engineering become your compass during your journey. And we like to turn talk into action. We're not named Action Engineering just for nothing. And we do that by bringing you deep expertise, breadth in our approach, and genuine feedback. So we'd love to talk to you further, or if you'd like to learn how to partner with you to chart your path to a resilient 3D future, we'd love to chat. All right, Mark, will pass the baton of the webinar back over to you, and we can open the floor up for questions.
All right, good job, Jennifer. Thank you for that. So let's look at these questions. Yeah, maybe.
I do have a couple, and I can just repeat them out loud here. So the first one that I answered in the chat is from Jeff, says, I see you have a Metrotom. Yeah, we were excited to get that CT scan data and actually get it scanned, the real part. He says he's a Zeiss CMM programmer, so he's drooling. Very excited you're drooling. I mean, that's a good thing. And the question is, has MBD integrated well to your CT inspection process? So hopefully that workflow that we showed in the first video describes how the CT data was used. Particularly, we know that when we author the overall profile tolerance in the GD&T, that gets it provides a challenge to the quality department for performing that inspection in a robust and a streamlined way. So we particularly and specifically used the CT scan to evaluate the overall profile tolerance, because this surface was casted. So that was this surface here. And so we wanted to get that scan data, validate it, set it's yet to go. But if you notice, the tolerance was quite large. Let's see. I know a couple of you had some challenges with the videos. Again, you can see the full recording after this. Is that right, Mark? They'll have access to the full recording?
Yeah, it will automatically be sent to all attendees by noon tomorrow.
Awesome. Thank you. Let's see, another question. Is the QIF interface available for PTC Creo? Yes, it is. Those were not, I didn't make anything up. It would have been way too hard for me to make up that stuff I showed you in the demonstration. That is a plugin that is offered by CapVidia, one of the interoperability vendors out there that is doing great work. They take the native Creo data, they translate it into a QIF format, and then that enables all the downstream processes that you saw. Okay, new question here, just checking my time. It just says, the second video talked about getting approval for model changes. Does the QIF software you mentioned cooperate with PDM vaults to recognize permit changes? So QIF is a standard, it is not a software. There is software that is created that allows you to create QIF standardized data. I have to recall my work. We're doing some interoperability mapping with the SAE S9102B forum, and there are spots within the QIF standard to approve, to capture approval information. So, meaning whatever you do in your PDM vault or your PLM system, you would be able to leverage that data, probably primarily through metadata or attributes that would source from your PDM and sync it through the process so that that data remained persistent. So the short answer is yes, definitely that approval remains persistent with the QIF data if you chose to set it up that way. But you're going to retain approval processes on the PDM and PLM side because that's what those systems are set up to do. So hopefully that answers that question. All right, next question. Okay, thanks, Jeff. How is the version control for the master QIF being maintained? Is the master in NVDA? No, master is definitely in your native CAD model and your PDM vault side. You always want to keep your master data sourcing from the root. And so that root is your native CAD data. QIF is a derivative data set. It can be authorized for use with an inspection. Some are even looking at authorizing it for use in manufacturing, but it's an authorized derivative. CAD, original native files, always your source and master data. So hopefully that answers that. Let's see, very good presentation. Thanks, David. So clear that he doesn't have any questions. Shucks. Okay, I should have left Easter eggs in there for you, David. All right, well, if you have further questions or you think, oh, well, what if I did X, Y, and Z, you know, let me know. I was actually afraid of that.
All right, great. So we're not seeing any more questions right now. So I want to take this opportunity to thank Jennifer for, I have to say ditto on the great presentation part. Very, very clear. And I think that the few questions asked really are a testimony to how clear many of those points were. So thank you for that. We certainly appreciate that. And anyone that has other questions can check back with Jennifer with the email that's already been, that she already gave you on the,
yeah, I can go back to
slide
that.
before this one.
Yep, I can go back to that contact page. Yep, feel free to reach out. We'd love to talk to you further.
Okay, so it's, Jennifer, thank you. And
Thank you.
So this is our second year for doing these QIF coffee chats. And one of the things that we've learned from last year was that in summertime, it's more difficult for people to attend these webinars because summer vacations or, you know, not only yourself, but others in your organization. And so what we're going to do for this year, the coffee chats are going to be going on summer vacation. We'll be off for July and August, and we'll be resuming coffee chat webinars in September. If you heard about this webinar series, then you'll be seeing this by way of the same notifications what and when the next coffee chat webinar is going to be, which it's going to be in September. So I don't have a calendar in front of me, but basically that will help you line up your calendars to attend the next QIF coffee chat. So since we don't have any more questions, I want to again thank Jennifer and thank all of you for your time today. And we'll see you all in September. Don't forget to look for that video that's coming by email tomorrow. All right. Thanks, everyone. Bye now.